Okay, up to now we've talked about estimating regression functions for quantitative response, and we've seen how to do model selection there. Now we're going to move to classification problems, and here we've got a different kind of response variable. It's what we call a qualitative variable. For example, email is one of two classes, spam or ham, ham being the good email. And if we classify in digits, it's one of the classes 0, 1 through up to 9. And so it's a slightly different problem. And our goals are slightly different as well. Here our goals are to build a classifier, which we might call C of X, that assigns a class label from our set C to a future unlabeled observation X, where X is the feature vector. We'd also like to assess the uncertainty in each classification. And we'd also like to understand the roles of the different predictors amongst the X's in producing that classifier. And so we're going to see how we do that in the next number of slides. Okay, to try and parallel our development for the quantitative response, I've made up a little simulation example. And we've got one X, one Y. The Y takes on two values. In this example, the values are just coded as 0 and 1. And we've got a big sample of these Ys from a population. So here, each little vertical bar here indicates an occurrence of a 0. The orange vertical bars as a function of the X's. And at the top, we've got where the 1s occurred. Okay? So this scatter plot's much harder to read. You can't really see what's going on. And there's a black curve drawn in the figure. And the black curve was what actually generated the data. The black curve is actually showing us the probability of a 1 in the model that I used to generate the data. And, so up in this region over here, the high values of X, there's a higher probability of a 1. It's close to 90% of getting a 1. And so, of course, we see more blue 1s there than we see 0s down there. And even though it's hard to see, there's a higher density of 0s in this region over here, where the probability is 0.4 of being a 1 versus a 0, where it's 0.6. Okay? So we want to talk about what is an ideal classifier C of X. Okay, so let's define these probabilities that I was talking about. And we'll call P sub k of X, this quantity over here, that's a conditional probability that Y is k given X equals X. In this case, we're just looking at probability of 1 in the plot. We've just shown the probability that Y is 1. There's only two classes, but in general there'll be, say, capital K classes. And there'll be capital K of these conditional probabilities. Now, in classification problems, those conditional probabilities completely capture the distribution, the conditional distribution of Y given X. Okay? And it turns out that those also deliver the ideal classifier. We call the Bayes optimal classifier the classifier that classifies to the class for which the conditional probability for that element of the class is largest. It makes sense. You go to any point, so here we've gone to point 5 in the X space, and you look above it, and you see that there's about 80% probability of a 1 and 20% probability of a 0. And now we're going to say, well, if you were to classify to one class at that point, which class would you classify to? Well, you're going to classify to the majority class. Okay? And that's called the Bayes optimal classifier. Here's the same example, except now we've only got a handful of points. We've got 100 points, having one of the two class labels. The story is the same as before. We can't compute the conditional probabilities exactly, say, at the point 5. Of course, in this case, we may have we've got one 1 at 5 and no zeros.
So we send out a neighborhood, say, and gather 10% of the data points, and then estimate the conditional probabilities by the proportions, in this case, of ones and zeros in the neighborhood. And those are indicated by these little bars here. These are meant to represent the probabilities or proportions at this 0.5. And again, there's a higher proportion of ones here than zeros. I forgot to say that in the previous slide. That's the same quantity over here. That's indicating the probabilities of the ones and the zeros. This is exact in the population, and here it is estimated with the nearest neighbor average.
So here we've done the nearest neighbor classifying in one dimension, where we can draw a nice picture. But of course, this works in multiple dimensions as well, just like it did for regression. So suppose we, for example, have two x's and they placed in they lie in the floor, and we have a target point, say this point over here, and we want to classify a new observation who falls at this point. Well, we can spread out a little, say, circular neighborhood and gather a bunch of observations who fall in this neighborhood, and we can count how many in class 1, how many in class 2, and assign to the majority class. And of course, this can be generalized to multiple dimensions. Then all the problems we had with nearest neighbors for regression, the curse of dimensionality, when the number of dimensions get large, also happens here. In order to gather enough points when the dimension's really high, we have to send out a bigger and bigger sphere to capture the points, and things start to break down because it's not local anymore.
So some details. Typically, we'll measure the performance of the classifier using what we call the misclassification error rate. And here it's written on the test data set, the error is just the average number of mistakes we make. Okay? So it's the average number of times that the classification, so C hat at a point xi, is not equal to the class label, yi, averaged over a test set. It's just the number of mistakes. So that's when we count a mistake, mistaking a 1 for a 0 and a 0 for a 1 as equal. There are other ways of classifying error where you can have a cost which gives higher cost to some mistakes than others, but we won't go into that here. So that Bayes classifier, the one that used the true probabilities to decide on the classification rule, is the one that makes the least mistakes in the population. And that makes sense if you look at our population example over here. By classifying to a 1 over here, we're going to make mistakes on about 20% of the population, of the conditional population at this value of x. But we'll get it correct 80% of the time. And so that's why it's obvious we want to classify to the largest class. We'll make the fewest mistakes. Later on in the course, we're going to talk about support vector machines, and they build structured models for the classifier C of x. And we also build structured models for representing the probabilities themselves, and there we'll discuss methods like logistic regression and generalized additive models. The high-dimensional problem is worse for modeling the probabilities than it is for actually building the classifier. For the classifier, the classifier just has to be accurate with regard to which of the probabilities is largest. Whereas if we're really interested in the probabilities themselves, we're going to be measuring them on a much finer scale. Okay, we'll end up with a two-dimensional example of nearest neighbors. So this represents the truth. We've got an x1 and an x2, and we've got points from some population. And the purple dotted line is what's called the Bayes decision boundary. Since we know the truth here, we know what the true probabilities are everywhere in this domain. And I've sort of indicated all the points in the domain by the little dots in the figure. And so if you classify according to the true probabilities, all the points, all the region colored orange would be classified as the one class, and all the region colored blue would be classified as the blue class. And the dotted line is called the decision boundary. And so that's a contour of the place where, in this case, there are two classes. It's a contour of where the probabilities are equal for the two classes. So it's an undecided region. It's called the decision boundary. Okay, so we can do nearest neighbor averaging in 2 dimensions. So of course what we do here is at any given point when we want to classify, let's say we pick this point over here, we'll spread out a little neighborhood, in this case until we find the 10 closest points to the target point, and we'll estimate the probability at this center point here by the proportion of blues versus oranges. And you do that at every point, and if you use those as the probabilities, you get this somewhat wiggly black curve as the estimated decision boundary. And you can see it's actually, apart from the somewhat ugly wiggliness, it gets reasonably close to the true decision boundary, which is, again, the purple dashed line, or curve.
Okay, in the last slide we used k equals 10. We can use other values of k. K equals 1 is a popular choice. This is called the nearest neighbor classifier. And we take literally at each target point, we find the closest point amongst the training data and classify it to its class. Okay, so for example, if we took a point over here, which is the closest training point? Well, this is it over here. It's a blue, so we'd classify this as blue. Right, when you're in the sea of blues, of course, the nearest point is always another blue, and so you'd always classify as blue. What's interesting is as you get close to some of the orange points. And what this gives you, you can see that the boundary here is a piecewise linear boundary. Of course, the probabilities we estimate is just 1 and 0, because there's only one point to average, so there's no real probabilities. But if you think about the decision boundary, it's a piecewise linear decision boundary. And it's gotten by looking at the bisector of the line joining, separating each pair of points when they're of different colors. So you get this very ragged decision boundary. You also get little islands. So for example, there's a blue point in the sea of oranges here. So there's a little piecewise linear boundary around that blue point. Those are the points, the points that are closest to that blue point, closer to the blue point than the oranges. Again, we see the true boundary here, or the best Bayes decision boundary is purple. This nearest neighbor average kind of approximates it in a noisy way. On the other hand, you can make k really large. Here we've made k 100, and the neighborhood's really large. It's essentially, there's 200 points here, so it's taking half the points to be in any given neighborhood, right? So let's suppose our test point was over here. You know, we'd be sending out quite a big circle, gathering 100 points, getting the proportion of blues, the proportion of oranges, and then making the boundary. So as k gets bigger, this boundary starts smoothing out and getting less interesting in this case. It's almost like a linear boundary over here and doesn't pick up the nuances of the decision boundary. Whereas with k equals 10, it seemed like a pretty good choice, and it kind of approximates the decision boundary pretty well. Okay, so the choice of k is a tuning parameter, and that needs to be selected. And here we show what happens as you vary k, first on the training data and then on the test data. So on the training data, k tends to just keep on decreasing. It's not actually monotone, because we've actually indexed this as 1 over k, because as 1 over k gets big, let's see, k large means we get high bias, so 1 over k is small. So this is the low complexity region, this is the high complexity region. Now you notice that the training error for 1 nearest neighbors, which is right down at the end here, 1 over k is 1, is 0. Well, if you think about it, that's what it's got to be if you think about what training error is. For the test error, it's actually started increasing again. This horizontal dotted line is the Bayes error, which is, you can't do better than the Bayes error in theory. Of course, this is a finite test data set, but it actually just touches on the Bayes error. It starts decreasing, and then at some point it levels off and then starts increasing again. So if we had a validation set available, that's what we'd use to determine k. So that's nearest neighbor classification. Very powerful tool. It's said that about 1/3 of classification problems, the best tool will be nearest neighbor classification. On the handwritten zip code problem, the classifying handwritten digits, nearest neighbor classifiers do about as well as any other method tried. So it's a powerful technique to have in the tool bag, and it's one of the techniques that we'll use for classification. But in the rest of the course, we'll cover other techniques as well. In particular, there's support vector machines, various forms of logistic regression, and linear discriminant analysis.